since increased the amount of hard drive space, as well as doing some other things. So when you check whether I'm recording, now you have to check whether there's enough space too. Just double checking. Okay. All right. So let's go back to the homework assignment that is due today. Are there any questions about that homework assignment? No questions? So I'm going to do the homework assignment just to show you the solution to that homework assignment, the one about the subtraction, the 4-bit borrow look ahead subtractor. And I'm going to use my own 4-bit look ahead, carry look ahead adder as the basis. That's part of the reason why I did it last time. So I'm going to put it into my downloads folder, and I got LogicSim already starting here. So we'll just go ahead and go to that folder and start with that. So we'll start with look ahead adder 4. Okay, it's complaining because I used the other LogicSim to do it.
You need to use the evolution.
Yeah, so now it's, it needs evolution to do it. So the two versions are not exactly compatible with each other. Darn it. Okay, there we go. All right, so this opens up just fine because, if I use evolution to create it, I have to use evolution to open it, and vice versa. All right, so the way you change this into a subtractor is the most difficult part is changing these guys. So that C in becomes B in, borrow in, and this becomes the difference, which is not the sum, right? And this becomes borrow out instead of carry out. Okay, so I think I got all of those taken care of. If I want to, I can fix this one too. Go ahead and fix this one so that it's not doing the sum anymore. This is, oops, oh, I just did one more. One too many delete. Okay, we're deleting at the wrong place. Okay, one more time. So this is selected, this is here. Oh, that's why, because I moved my mouse. Yeah, like once I move it outside of the text box, it becomes deselected from here. So it's a good time to ask the department to give me a different keyboard. Because I like to use the eraser thing. It's called a touch point. It's only available on certain computers, and I think even Lenovo is moving away from that. But that's actually one of the best pointing device as far as I'm concerned, because you never have to move your hand at all. Because that pointy thing is between the keys G, H, and B on the keyboard. If you have a computer right in front of you, you know what I'm talking about. So you just kind of touch that thing, and push it, in whatever direction you want the cursor to move. And there's no motion whatsoever. Nothing actually moves, right? You're just applying pressure, and it's really one of the best user interface as far as I'm concerned. Okay, but here I have to use a mouse. All right, so I got most of these things, done, and then the only thing left to do is to change the G and the P's. Okay, you have to negate the first input, the X, and you're done. Okay, so we have to go here and say negate the top, yes, and then we go here and say, we want to negate the top. And if you don't like this because it's not looking good, you can always just go ahead and change that. It's selecting more than it needs to. Let me see if I can just select that one segment. It's going to work okay. It's just it just doesn't look very good. There we go. Okay, can we get rid of this? Get rid of this. Get rid of this. It's really just to make it look nice at this point. And we can do the same thing over here. That fixes it. All right, so the question is it working now? Well, obviously we have to test it. So the test is going to be, all zeros, and then the output should be all zeros. That works, good. Then we have 1 minus 0 should be 1, right? Whatever minus 0 is, whatever that thing is. That's good. 0 minus 1 should be 1, 1, 1, 1 with a borrow. And it is 1, 1, 1, 1 with a borrow. So you can go ahead and check, most of the other ones, but I think, that should work just by negating the first input to the G and the P gates. Okay, that's it. That's the only difference between an adder and a subtractor from the functional perspective. The rest is just changing the labels and whatnot. So are there any questions about the solution to this homework assignment? No questions? Okay. Excellent. All right, so what we'll be talking about today will be the first type of memory units in a computer, which is known as we'll start with what we call a latch, and then we'll move on to a flip-flop, okay? We also have the concept of a RAM module here, but I think I'm going to move the order of the topics just a little bit, so I'm not going to talk about RAM until we are done with talking about memory itself, which is this unit here. It looks like a quiz, but it's not really a quiz. So when you click on this, it will look like a quiz because it will say, okay, do you want to take an attempt? But it doesn't really matter because the score that you get out of this quote-unquote quiz does not add to your actual final score for this class, and you can retry as many times as you want. Okay, there's no time limit either. It really is kind of intended as a somewhat interactive instructional material, so that after reading one page, there's a question you can answer, so it's kind of interactive, and you can double check whether your understanding of the material of that page is correct or not. Okay, but other than that, it really is intended as reading material, not intended as a quiz. Okay, so what we are looking at here is something that looks like this. We have two NAND gates because you can see that it is for the most part the shape of an AND gate, but with a bubble as the output, so it's negating the output of an AND gate, which makes it a NAND gate. Okay. So when you look at something like this, the only difference between this setup and all of the other circuits that we have seen up to this point is there's a feedback. Okay. The output of the top gate becomes the input, or one of the inputs of the bottom gate. The output of the bottom gate becomes a part of the input of the first gate. Okay. And this is the first time we see something like this, okay? Where the output goes back into the input, and they seem to be interlocking, okay? Are there any questions about the schematic or the picture or how things are connected? And for the first time, this cannot be translated into a Boolean expression, because Boolean expressions cannot handle that feeding back mechanism. So we cannot turn this into a Boolean expression anymore. Whereas before, when you look at the adder or the subtractor, we can express everything as a Boolean expression, but not this one, okay? So for this one, when we analyze this, it's going to be a little bit different because, in addition to giving it all of the potential inputs, 0, 0, 0, 1, 1, 0, 1, 1, we also have to take into consideration, quote unquote, the state of this circuitry itself, okay? All right, so what we'll do is I'm going to run LogicSim but on a piece of paper because I want us to have an opportunity to think about it, to think about what the circuit is going to do when we present a certain input to the whole thing. So we'll go ahead and do it this way. I have the document camera ready, and we'll go ahead and look at the circuitry from the perspective of a static circuit. Okay. So I'll redraw exactly the same circuit here. Okay, we have one NAND gate here, another NAND gate here. One input to each is from the outside. The output is going to the outside also. Question? Oh, okay. Slide it over. There we go. Thank you. But the output of each one becomes the input of the other one. Okay, and this is the first time we see something like this. And the result of doing this is very significant because we have the smallest unit of quote-unquote memory in a computer at this point. Okay. And I will start to label these things. Okay, the labeling may not be the same as in the notes itself. So we'll call this, I'll call this X and Y, and then this one I'll call it A and B. Okay, so it may not be exactly the same way that I label the outputs and the inputs, But it doesn't really matter because all we need to do is to see how A and B relate to X and Y. Okay? All right. Now, because this is a NAND gate, okay, it is essentially still having an AND gate inside it. It's just negating the output, which basically means if the input to any of these gates, if any input of any gate is a 0, the output is going to be a 1. Okay? Because it is inherently a negated AND, and with any type of AND, if any one of the input, at least one input is a 0, the output is going to be a 0. But in this case, because it is negated, an output of 1 of an AND gate is the output of a 0 of an AND gate becomes an output of a 1 out of an AND gate. Okay? So we'll work out the easy ones first. Okay? So these are the inputs, X and Y. Okay? If X is 0 and Y is 0, then the output A and B are fairly easy to work out because at least one input to each of the NAND gate is a 0. The output of both of them are going to be
0.
1s, okay? Because they are negated, okay? No problem,
Oh, yeah.
easy peasy, right?
Yeah.
Okay. Well, the hard one is this one, okay? I'm going to put this one all the way here, but we'll talk about it. What if X is 1 and Y is 1? Then we have a big question, don't we? Because if X is 1, Y is 1, then we are looking, okay, let's take the top gate into consideration. Let's take this guy into consideration. X is 1, great, okay? But what about the other input? I didn't say anything. Well, is the other input determined by Y? Let's take a look at Y. Y goes to the bottom NAND gate and is experiencing exactly the same problem. Because if I just guarantee that Y is a 1, I have no idea what is the output of the bottom NAND gate. Because now it is solely determined by the output of the upper NAND gate. Is that making any sense? Okay? So if X is 1, Y is 1, okay, I can only say that the circuitry will maintain A and B the way they were. It cannot change. Is that okay?
I didn't get it.
Sorry?
I didn't get it.
Okay. So whatever the state was before, okay, it has to maintain that state.
Okay.
Okay? But there's one state that it cannot be in. Which one is that? There are two states it cannot be in. So let's take a look at this particular configuration. Okay, X and Y are both 1s. Okay, so I'll put it up here. Let me slide this over and put a new table here. So assuming X is 1 and Y is 1, okay, the question is what's going to happen to A and B? Okay, what's going to happen to A and B? So we'll use old A, old B here, and the current A and the current B over here. In other words, these two is representing what the states of A and B prior to X and Y becoming 1s, and this is after X and Y becoming 1s.
Right.
Is that okay? All right. So there are 4 possible ways, right? Because old A can be a 0, old B can be a 0.
Yes.
Okay. But A and B cannot be both zeros at this point. Why can't they both be zeros?
One's negated by the other.
Yep. So it's not possible. Okay, so this is one of the scenarios where we have no idea what's going to happen here. Okay, let's take a look at the second one. What if A was 1, B was 0? Then what's going to happen to A and B when X and Y are both 1s? Well, think about it. Okay, so let's go ahead and simulate. A is already a 1, was a 1 already. Y is also a 1, so you have 1 and 1, which is 1. But since this is negated, B is going to be a 0. But B was a 0 already, so we have no state change for B. What about state change for A? Okay, X is a 1 to begin. X is a 1 to begin with. B was a 0 to begin with. 1 and 0 is a 0, but you negate it, so that means A is going to be a 1. But A was a 1 already, so there's no state change in this case. A maintains its state as 1, B maintains its state as a 0. Is that okay? And if the old states are reversed, old A is a 0, old B is a 1, same scenario. Because A and B are pretty much symmetric. Is that making any sense? So now we have one last case. What if A and B were both 1s to begin with, and then we have X and Y being both 1s? What's going to happen to A and B? The question is, can they both be 1s? They cannot be both be 1s, right? Why not? Okay, well, let's take a look. So X is 1, Y is 1. So X is 1, and in this case, A is 1 as well. So this is 1 going into here. B is 1 also. So this is also 1, right? So I have 1, 1 as the input of the top gate, but because this is a NAND gate, it has to be a 0 here. Okay? But once we have this as a 0, B can be a 1. B can maintain its state as a 1. So now the question marks are here again, because we have no idea which one is going to switch to a 1 and which one is going to switch to a 0. But we know that one of them is going to be a 1 and one of them is going to be a 0. Okay? And the same thing happens with the first one. When A and B were both 0s to begin with, then which is not possible. Okay, this one is actually not possible, so we can pretty much rule out this row here, because there's no way out of these 4 to ensure that A and B are both 0s. So this one is out of consideration, but this one is still in our consideration. So if someone were to build a circuit like this, and switch from X, Y being both 0s to begin with, which makes sure that A and B are both 1s, and then switch X and Y both from 0 to 1 at the same time, the question is which one of A is going to become a 0 and which one is going to become a 1. We know one of them is going to be a 0, the other one is going to be a 1. The question is which one? So how do we answer that particular question? Is it the luck of a draw, or is there some other factor that will determine, pretty much deterministically, which one is going to be a 1 and which one is going to be a 0?
Be the length of the circuit?
Yep, it's going to be the propagation of delay. So depending on, assuming these circuits are not truly identical and symmetric, if one circuitry just takes a little bit longer to complete the calculation, that will determine, which one is going to be affecting which other one. Okay, so the faster one is going to be, yeah, go ahead.
Oh, I'm following along with Logician, and I just did that. It said oscillation apparent.
It is not going to oscillate, because once one is a 0 and the other one is a 1, it will settle, it becomes stabilized. It's not going to oscillate in this case. Logician will tell you it is going to oscillate because it is basically having 2 possible paths of state change, and both of those are possible depending on which one switches first. But it's not going to oscillate.
Okay.
Because once you settle to one being 1 and the other one is a 0, it becomes a stable state, and it's not going to switch again.
Okay.
In other words, if you look at a physical problem, what we have here is you have a situation like this, okay? And if you tip it one way or the other way, the ball is going to roll down one side or the other side. It's not going to swing. If you have a different scenario, which is like this, and you're basically putting in energy into the system, then it will oscillate. But not in this case. This one is not going to oscillate. This one actually is not a good picture. I think the better picture is a string holding onto a ball. So when you push the ball on one side and you release it, it's going to swing between the two sides. But in this case, it's not going to swing. It will just go into one side and stay on that side.
Do they solve that in Logician evolution, so it lets you do stuff like that, or have you not tested that?
I think Logician evolution is supposed to have a better detection logic of oscillation. So did you use evolution or the standard?
No, this is still the old Logician.
Yeah, if you try in evolution, it might give you a different answer. Okay. And then the key also is you have to switch from xy being zeros to xy being ones at exactly the same moment. If you switch one first, then it will go to one particular steady state. Okay? So this is our smallest unit of memory because because this state here, x and y both being ones, preserve the state of A and B. Okay? If A was 1, B was 0, then x, y being both ones will preserve that state. If x was 0, b is 1, it will preserve that state as well. Now if A and B are both ones to begin with, then we have a race condition. It's called a race condition. It depends on which gate is slower, then it will affect the outcome. And race conditions are really bad if you're designing real circuits because it will give you a quote-unquote deterministic result, but only because of the implementation, only because of certain transistor paths are longer or having a longer propositional delay. So when you change the die process, when you change the size of the transistors, then it will change again.
So it's not something you can take advantage of and utilize?
Yeah, you don't want to take advantage of a race condition. You want to remove race conditions. Or if you do have race conditions, you want to publish the standard and say that there is a potential race condition, so you want to get around that problem and say that, like in this case, just say that, do not get into this scenario, the outcome is undetermined. Yep, go ahead. I thought that was a question. Good. Okay. So are we good on this one so far? Okay. Well, in terms of race condition, I can tell you one story from my past career about the race condition. Okay, so this is okay. Let me see if I can find the references to it. So this is the Zilog Z180 processor. It has to do with an MSB, low SB, LSB, least significant byte of some kind of 16-bit register. So let me see if I can just use these words to find which one I'm looking for. And it doesn't, well, I'm not gonna spend too much time to look for it. Okay, so basically this is a 8-bit processor. And even though the processor is an 8-bit processor, some of the registers inside, some of the mechanisms inside are 16-bit wide. Okay, so how do you change a 16-bit thing when you can only write 8-bit at a time? Well, the answer is pretty easy. You write to either the most significant byte first, and then you write to the least significant byte, or you reverse the order, right? Well, as it turns out, the hardware has a lock mechanism, but only in one direction. So if you change the least significant byte first, it will lock the use of the most significant byte, so it won't cause any problems. But the other way around, may potentially cause a problem. So the software, the manual recommends and say that you should only do it in this way. Okay, change the either least significant byte first or change the most significant byte first. So what if someone is to ignore this advice from the manual and do it the other way? Well, the other way triggers a race condition. Okay, it triggers a race condition. So what is so bad about the race condition? The problem is it worked for the most part.
You don't see an error because it works.
You do not see an error because the propositional delay made it seem that it's working. Because the race, the correct component wins the race in that case. Okay, so it appeared to be working even though it's written in the wrong order. So how is this problem going to show up as a problem when they change the die size? Okay, so at one point in time, Zilog changed the die size or changed the transistor technology. So Intel does it all the time, right? They change from 25 nanometer to 18 nanometer and so on and so forth. And Zilog did the same thing, except very much less frequently, but they did change. Okay, So the processor is still exactly the same processor, it will still be specified exactly the same way, but because the size of the transistors have changed, it also changed the raise condition. So the proper component in this case is losing to the wrong component, and then the problems start to show up. Okay? But from the manufacturing perspective, if you run a company and you're selling some product, and then the software in the product has this problem, how is it going to show up? Well, your product will work for years, and then one day, just because you get a different batch of processors, everything that you ship out stopped working. And that's exactly what happened when I worked for this company called Z-World in Davis. Can you imagine how much problem, as far as the company is concerned, this is going to cause? Every single product that we had was based on the same processor, and the code, the incorrect code, is in the BIOS, so to speak. Okay, it's the firmware. This is basically what runs when it wakes up from power up. So all of our products stopped working. And then they ask us, the engineers, and go like, what's happening? Everything is not working, and our customers are screaming, right? What do? You go find the engineers, right? The hardware engineers will just basically say, oh, Silog says the new chip is functionally identical to the old chip, not my problem. So who's left to ask? The software people. And guess who's in charge of software development at the time? Yes. Yes. My boss called me the director of software development. I call myself the responsible one. If there's anything wrong, find me. I'm responsible. So they found me and said, okay, this is a problem. Okay, you guys are going to fix this. And obviously, the marketing people have to make promises to the customers like, oh, we'll get it fixed in 2 days, 3 days, whatever, right? They have to make some promises. So when after day 2, and I was very diligently going through the code to find the problem. So after day 2, obviously the marketing manager, who was an quarterback playing football. Okay, so he's like a 6'1", 6'2" big guy, and he comes to my office and go, Tech, how's the progress? I'm still working on it. When is it going to be fixed? And I only answered the only way I could. It is fixed when it is fixed. And he didn't quite like that answer. But that was the only answer I can give him. I cannot give him an estimate whatsoever. If I can say, if I can name a time frame, I would be lying. Because this is not the kind of problem. It's not like, manufacturing where you can just step out with something and you can time and say, okay, it takes me X amount of time to make one. If I need to make 100, it just multiply that by 100, right? This is not one of those things, okay? So I just told him, it's done when it's done. I cannot tell you when it's going to be done. And he got really pissed, and then the sales manager came in to basically tell this guy, the quarterback, to back off. It's like, if you keep bugging tech, it will take even longer. It's not gonna help. So leave him alone, let him do his job. And then found it, the next day, it didn't take me that much longer to actually find the problem. But it was very intriguing because this one had been there all along. But because of the race condition favoring the right component before, it never showed up. And then when they changed the die, changed the process of the die, changing the size of the transistors, then it showed up, just out of nowhere. So that's why I just want to give you an example of what race conditions can do. It can give you, it can make the product seems like it's working, even though it is just marginally working in the right direction. But as soon as you change like little things in the process, in the die, in the transistor size, the problem will show up. So that's why, if you're going into computer engineering or electrical engineering, you want to eliminate race conditions. And if you cannot eliminate race conditions, you need to let people know, and so that people can use other means in software to get around a potential of getting into race conditions. Okay? All right, so getting back to our usual content. Okay, so let me go back to the document camera. All right, So this is our smallest unit of memory. And if you go to the slide in Noodle, the reading material, the question is, does this configuration end up with a fight where two outputs can specify different values to the same input? Well, let's see whether that is even possible, because we are looking at two outputs connecting to the same input. This output connects to this input here, but this input doesn't receive anything else from anywhere else, okay? Not a problem. This input here is only receiving the output of this gate, but it's not, there's no potential of any fight. So the answer is no here. So are there any questions of why there is no potential of a fight of any kind in this particular circuit, even though I'm taking the output of one to become the input of the other one? No questions? Okay. So let's move on to the next slide. So the next slide, basically, okay, I flipped the AB and the XY, but basically it's the same thing. So it explains, the truth table of an SR latch. Okay, so there's a reason why it's called an SR latch. S is set, R is reset. Okay, so one is quote unquote setting the output, and the other one is resetting the output, which doesn't seem to make any sense because the outputs are symmetric as well. So if you're setting one and resetting the other one, but you can turn it around and say, but if I look at it from the perspective of the other output pin, it will be exactly the reverse. So that's just a nomenclature here. So if both of the inputs are ones, then we have no change to X and Y. They are the negations of each other. But if they were both ones to begin with, then you have to rely on the raised condition to determine which one would turn into a 0. If A is a 1 and B is a 0, which in our hand-drawn picture, the X and the Y's are opposite to the AB's, so this is just the inputs. So this will change the state, okay? In other words, going back to this circuit here, if I fill in this table, if I say X, what if X is 1, okay, and Y is 0 over here? That will basically, determine A and B in a deterministic way. There's no raised condition whatsoever in this case. Because if X is 1, okay, and Y is 0, then we guarantee the output of the bottom gate to be a 1. Okay, so we are now guaranteeing that B is going to be a 1. But when B is going to be a 1, X is a 1 already, A is guaranteed to be a 0. So there's no question whatsoever of what's going to happen in this case. In other words, this configuration of the input, X being 1, Y being 0, is overriding the memory unit. It's not maintaining the memory. Instead, it is now setting the memory in one state instead of the other state.
How come that's different than the table you wrote before?
You mean the other table being this one here?
Yeah.
It is, okay, this one is based on, you're having X being 1, Y being 1. So if
Old values.
they're holding the value. So the X, Y both being 1 means do not change the state of A and B, of the outputs. When X is 1, Y is 0, it means change A to become a 0, change B to become a 1. Is that okay? And then the other way around is having a 0 for X and a 1 for Y, then it will do exactly the opposite.
Yeah.
So X being a 0 guarantees A to be a 1, and because A is a 1, Y is a 1, it guarantees B to be a 0. So in this case, it is deterministically changing the state to 1, 0 as far as A and B are concerned. Is that okay? And then the last one, which is this one here, is basically just holding A and B. So A would be the same as before, B is the same as before, assuming they're not both ones before. If they were both ones before, then we have a raised condition, and then the raise will determine who becomes a 0 and who becomes a 1. So we'll just say maintained for the most part. Are there any questions about the SR latch? This circuitry is called the SR latch. Okay. No questions about that? Okay, I got a question. If this is called, yes, go ahead.
I didn't get it if the value of X and Y is 1 and 1, so it will be maintained. What does it mean? Like
It means you look at this table. It means look up that table.
Yeah,
If A
yeah.
was as 1 before, B was a 0 before, they get to maintain the state.
Right.
If A was 0, B was a 1, they get to maintain their state.
Right.
If they were both 1s before, then we have to use a race condition. We have to look at the actual latency of the gates to determine who's going to be 1, who's going to be 0, which is a scenario that you don't want to get into.
So
Yep.
What if there was no latency?
What if there's no latency?
What if they were the same, the calculations?
Exactly the same time? Okay, well, let's take a look. So if it takes exactly the same amount of time to make the output change according to the input in both cases, let's try to figure out what's going to happen. So they are both originally 1 and 1, and x and y become 1 and 1 as well at exactly the same moment. Okay, so that's the scenario. So that means that these two inputs are 1s, these two inputs are 1s as well, right?
Yeah.
And then you will end up with a 0 coming out of here and a 0 coming out of here at exactly the same time, right? So that will, in return, this 0 will propagate to this one here, and that 0 will propagate back into here, which will change both of these states to 1s. Oh, so that's why it is still an oscillation, because it's not an oscillation between A and B, it is an oscillation of both A and B's being 1s, and then they both become 0s, then they both become 1s, they both become 0s. That is the oscillation reported by LogicSim.
So does it just loop then?
It is a loop, yep.
Okay.
And the frequency of that flipping and flopping depends on the latency, because the latency of the gates now determine the exact amount of time it takes for the 1 to become a 0 and then for the 0 to become a 1. Yep.
In this scenario, the lines to the output are actually shorter than the lines back to the input. So would your outputs also oscillate in that case?
Yes. So A and B will both go from 0 to 1 and both go from 1 to 0 at exactly the same time. Yep. But that depends on the gates being completely identical. There's no there's no difference between the propagational delay. Yep.
So how do you simulate a race condition in LogicSim?
That's a good question. I do not. So how do you trigger it, or how do you actually simulate it?
Like how would could I add a component in there to simulate a race condition?
You need some kind of component that can directly let you specify and inject a latency. So that is what you need. You need a delay component. And in LogicSim, they might have a delay mechanism. So let's take a look. Gates. Nope, there's no delay type of thing here. Because if you look at buffer, it doesn't let you specify the latency or the delay. Plexers, I don't think plexers will help here. Memory, no, memory cannot help because that's deterministic. Yeah, I don't think there's any way to actually simulate latency in this particular case. Yep.
Not gates back to back.
But you cannot specify the latency delay of a NOT gate either.
But it would take longer for that one.
It would take longer, but you still cannot see the change of the signal. Because I think in LogicSim, the way it does the simulation is it relies on the dependency not getting into oscillation. So it's basically going with whatever is changing first, and then it propagates all those changes, and then it will say, okay, are we done? If any one of those things can go back and change the state of any component at the same time, then it will report back and say we have an oscillation, but it won't actually simulate the oscillation itself. So it will detect it, but it cannot simulate it. It's kind of like in a spreadsheet. Okay, so this is a good way to kind of answer that particular question. So it's kind of like in a spreadsheet. Let me see if I can go back to a spreadsheet. I don't want to mess up this one. Oh, wrong password. There we go. Okay, I just want to show you a spreadsheet that has kind of the same problem, but it becomes impossible to simulate. So you want to open the Google Sheet. So you basically have A being, okay, B1 plus 1, B1 plus 1, and then B1 is equals A1 minus 1, and it has a problem now. It's circular. So it's kind of the same thing, because even though we kind of know that they're just oscillating between the value next to it and then the value back, and a blank is basically a 0. So we should basically be able to see, both of these things, oscillating between 0 and 1, or -1 and 0, depending on which one is computed first. But the software refuses to do it because it now detects a circular dependency. And I think that's how Logisim works as well, is it can detect a circular dependency, and it just refuses to do it. When you look at the add circuitry or the adder circuitry, it doesn't have any type of dependency like that. And if you use an FR latch the right way, it doesn't generate this problem either, because the state, once it is in the state, it doesn't change once a particular pin settles, it doesn't change anymore because of another gate that was affected by it in the first place. So I think that is how it works. It detects that circular reference, and once it has a circular reference, it just says, oh, we have an oscillation problem, but it's not going to simulate the oscillation itself. So is that answering the question?
Yeah, I'm messing with it right now. I don't know like most of these components, but would there be a way to use like a clock and then some sort of like
A clock won't help either.
Okay.
Because in the case of the SR latch, it is not a clocked component. It is a combinatorial problem, and it is not clocked. And as a result, you can put a clock into here, but it's not going to give you the ability to simulate the oscillation. The only way to simulate the oscillation is to change the source code of Logisim so that you can actually specify the exact latency of the gate. Like how long does it take for a input change to become visible at the output. If you can specify that, then you have a chance of actually simulating the oscillation. But I don't think the software has that built in yet at this point. So I think we can see Logisim Evolution Plus at the end of this semester with the ability to specify gate latency so that we can simulate these particular problems. We'll make it extra credit, right? Okay, so this is great, good stuff. So getting back to the nodes, which is all the way here. Okay, there we go. So now the question is, knowing only that the input S and R are both ones, what is the state of Q? Okay, so we have changed the nomenclature just a little bit. X is usually denoted as Q, which is the output, and then A and B are known as /S and /R. Okay, so I know without the picture here, it's kind of hard to see. So what I'll do is I'm going to go back to this picture, and now we will start to label the input and the output correctly using that particular notation. So using that particular notation, and I will use a different color so that it is visible. Okay, that'll work. Okay, so this one here is known as /R or S over bar. Okay, so you can use one or the other notation. This one is known as /R or /R or R with an over bar. Okay, once again, use one or the other. The slash really means the same thing as a bar overhead. It's just that with certain type of text edit with a text editor, you can't do the over bar thing easily. So that's why we use a slash instead, because slash is easy to type.
Does the overbar ever get confused with negation?
The overbar is exactly negation here. That's what it means. Yep. Now, what about A and B? It is now determined that one of them will be Q, and then the other one is going to be Q bar or /Q. Okay. Okay, so what does it mean here? Okay, so when you look at the table, so we'll go ahead and change x, y, to this particular notation, and I will make it cleaner this time. So, I'm going to erase x and use the notation /s, and I'll erase y and use the notation /r. Okay, there we go. And we'll change a and b to q and q bar, or /q. So this is q, and this is /q, which is basically saying not q. Okay, there we go. All right. So what are we seeing? We are seeing that, out of the two middle rows, the third one, let me point out which one we are talking about. So we are looking at, oops. Okay, I'm putting a pen below the bar that we want to look at. Okay, so this is the row. So with this particular row, we can see that when /s is a 0, q is set to a 1. In other words, this particular row is quote-unquote setting the output. Yeah. Question?
I was going to say Q and /Q just look like S and R, like negated S and R.
They are basically opposites of each other, yes. So one of them sometimes is not even represented. The /Q sometimes is not even the output of a SR latch. It is only Q that is the output of the SR latch. So /Q sometimes is known as an internal state because it is not useful from the outside perspective. Okay? But this is why we put a slash before the S, because it is setting the output, but it is negated. In other words, normally we say one is setting something, but in this case, this is what we call an active low signal, which means a 0 means that's what we want to do. Is that okay? Yep.
It's weird seeing Q on when S and R are both zeros, Q and not Q are both 1.
Mm-hmm.
So how can not Q, why is it called not Q if it's not Q?
It is just because the top row is not used much.
Okay.
Because you normally would not have /s and /r both being zeros. Because what it really is saying here, because when you look, if you take the slash into consideration, it basically means a 0 means you want that, right? So /s means if it is 0, you want to set the output. /r means if it is a 0, you want to reset or clear the output. The output is Q itself. /Q is the negated version of the output. Okay? So if you look at it that way, it doesn't really make sense to try to set and reset at exactly the same time. So that's why the first row is typically not used except for very rare cases. Now, but it does make sense for the last row. The last row is basically saying we are not setting and we are not resetting. Oh, what does that mean? It means we are maintaining. Just keep the state of Q the same way as before. If it was a 1, keep it as a 1. If it was a 0, keep it as a 0. Yep. Mm-hmm.
So, which of the Q's is like the main state versus both of them?
They are both the states. Okay, even though they are basically negations of each other, they're both needed in order for the SR latch to work. Now, you can ask which one really matters to the outside world. Then you can say, well, maybe in most cases we don't need /Q. But in order for the SR latch itself to work, you still need that output from the bottom AND gate. So you can do this, okay, in the circuit. You can basically just, let me see if I have a little bit of paper here. So in an actual circuit, what you can do is to do this. Don't even bring the output of the bottom NAND gate out to a pin. That's possible. If it doesn't help you in any way, then you just say, yes, this is completely internal to the circuit, and then from the outside perspective, you have no access to /Q. Okay? That's okay. But the output of the bottom NAND gate is still a very integral component of the SR latch, because you need that to go back to the top gate to complete its function. Is that answering your question? Okay. So the setting and resetting is really from the perspective of Q itself. Are we setting Q or are we resetting Q? But because the negated nature of the setting and the resetting feature, that's why we have to put a slash before the S and a slash before the R, so that it is noted correctly, the polarity is correct. It's kind of like with a light switch, most of the time flipping the switch up is turning it on, right? So that's a normal switch. But when you have a switch that is installed opposite because the electrician did not know the standard and install the switch upside down, all you have to do is to put a slash in front of that switch. Now you know, okay, to turn it on, you do this. That's basically what the slash means. It just tells you which way is on. Normally it is 1 is on. In the case of a slashed signal, 0 is on. That's all. Is that okay? Sort of? Okay. Yeah, this is also called, this type of thing is also called active low when it comes to electrical engineering. So when you look at the slash signal, sometimes we call it active low. Because a low voltage means, yes, this is what we want. And there are many signals on a computer chip that are, active low. The reset of the entire computer is usually active low, which means, for those of you who really looked into the circuit board and stuff like that, there's one particular trace that is called a reset line, and it's universal to the entire circuit board. It is an active low signal, which means if you use a voltmeter and you measure it, and you measure a high voltage, it means do not reset. The moment you ground that signal, you connect it to ground, to connect to 0 volt, your entire circuit board resets. And there are reasons why certain signals, other than this one, there are reasons why they're active low. It has to do with can I use multiple mechanisms to trigger the active signal. And anything that is active low is easy to deal with, because what they do, this is completely out of the scope of this class, but I think it is kind of useful to know why that is the case. So with the active low signal, what happens is normally they have what we call a pull-up resistor. So this is a positive voltage, I just call it VCC. In older computers, VCC is 5 volts, but they are really low these days. So it depends on what type of logic system you use. So this is an active low signal. So normally this really big resistor, or with a big value, is 10 kilo ohm, which is a very high resistance. So it has a very weak tendency to pull this particular line to VCC. But without any other mechanism in this particular setup, this line is going to experience VCC because nobody is going to tell it otherwise. Is that making any sense? How do you make this line, experience a low voltage? Well, an N-channel MOSFET will do it, right? This is an N-channel MOSFET without a bubble. Okay, how do we turn on an N-channel MOSFET? Can you remember? This is the source, this is the drain, this is the gate. The gate voltage has to be up higher than the source voltage, right? So when this gate has a high voltage, then this transistor turns on. What happens when the transistor turns on? It becomes a short, right? It is as if you're just connecting this line to ground. So when you have this line connected to ground through the transistor, remember this is a very weak pull-up. In other words, it's a very weak spring, barely hanging onto something, so that it's not all the way to the ground. So this is weak, this is strong. So that means this line will no longer experience VCC. Instead, it will experience 0 volt, which is ground. That's how you trigger a reset. But the best part is you can now have multiple things like this to trigger the reset. So if any one of these transistors thinks, oh, okay, I gotta reset the circuit, each one of these can reset the circuit independent to the others, and there's no fight whatsoever. Because the only thing it has to fight in order to bring this line to 0 volt is this transistor here, this resistor here, which is a very high value resistor, which means we have a lot of resistance. So it's not really having a lot of strength pulling the signal up to 5 volts or VCC. So what are these things corresponding to in an actual computer motherboard? One of these may be a reset button, an actual button that you press. Okay, so it's not a transistor, it's an actual button. Change the signal, change the component so that it becomes a actual button. Okay, so it's a button, you press, you complete the circuit, now you have the connection to the ground. The other ones, one of these is probably coming from what we call a watchdog circuitry. A watchdog circuitry is a very interesting one. In many computers these days, there's a watchdog mechanism. A watchdog mechanism is actually kind of like a dead man switch, okay? What it means is, unless the watchdog is hit within a certain amount of time, it will basically say, uh-oh, nobody is hitting me, something bad has happened, I'm going to reset the computer. So when the computer is operating correctly with healthy software components, the software component will set up a timer or some kind of mechanism to inform the watchdog and say, yep, I'm okay, do not reset. Yes, I'm okay, do not reset, and so on and so forth. Okay? And then this one here may be connected to a brownout detection circuit. So the brownout detection circuit is really, really important because the worst thing that can happen to a computer is not a blackout. A blackout is a clean cut of no power. Okay, you just lose all power and that's the end of it. No power, the computer stops working. No big deal. A brownout, on the other hand, means you're losing some power. The input voltage onto your transformer is going down, but not quite to 0. Okay, so normally we have 110, 115 volts. Maybe it's getting down to 65, 57-ish, that sort of thing. That is really bad for circuitry because at that point your circuitry can no longer truly distinguish between what is a 1 and a 0. So the function of your computer will now go haywire. So the brownout detection circuit is basically setting a threshold and say if the regulated voltage from your power supply drops below a certain point, it is considered bad. Just reset everything. Hold the reset line so that nothing works. They basically all stop. But when they all stop, it is a quote-unquote safe state because nothing is being done. You're not continuing to write anything to the SATA drive, which is probably a better thing than spewing out some random data to some random sector on your hard drive. Yep, go ahead.
I was gonna ask, this is kind of like the opposite, but for like a surge, like an increase in voltage, does that just go straight to the power supply, or does it?
A surge is usually arrested by a surge protector of some kind.
Like within the computer?
It can be within the power supply. It can also be outside of the power supply, like a surge protector.
Yeah.
So what they do is they use MOV components or metal oxide. I don't remember what V stands for. Varistor. Okay, thank you. So it's basically a self-sacrificing component where it just dies. In the case
Computers
of a
normally
surge.
don't have those, right?
It depends, I have no idea because it's an added expense. It's not like people do not know how to protect computers from surge. It's just that they need to add some additional components to do it. It also depends on how much energy you need to absorb, like in the case of lightning. So so all of those surge protectors are rated by kilojoules or joules, okay, which is a unit of energy. It's basically how much energy can the circuitry handle before it passes on the surge to the component that it is supposed to protect. But these days, since we have Google Drive, we're not too concerned about surges like that. You just go to the closet, break out another computer, plug it back in, log into Google again, everything continues, right? That's the way I want to set up all the homework assignments in this class. Okay, so did I answer your question? Okay, cool. All right, so getting back to here. Okay, so now we have explained the nomenclature of why it is called /s/r, q, and /q. So the question is, knowing only that the inputs S and R are both ones, what is the state of Q? The answer is we cannot know, but we know it is stable and maintained unless Q and not Q are both ones to begin with. Then it might go into oscillation. Okay. All right. So now we have a circuitry that looks like two SR latches stacking on top of each other, right? Because when you look at this circuitry, we have one SR latch here with the little negation here, okay? Other than that, it looks like exactly like an SR latch. And then we have a proper SR latch here, okay? So this is called a clocked signal. This is called a clocked flip-flop or D flip-flop that is clocked. And you can see from the input, the second one is called CLK, which is the abbreviation of clock. The first one is called D, which is data. Okay? So now we have a different circuit that is a little bit more useful to us. Okay, so let's go ahead and take a look at this circuitry and try to think about, okay, what's going to happen? First of all, what happens when clock is 0? So just kind of imagine, in this case, clock is 0. So this would be a 0, this would be a 0, which automatically turn these two into what? Ones, exactly. So if the second part of this circuitry, which is this part here, is a regular SR latch, what is going to happen to the SR latch when CLK or the clock signal is a 0?
Maintain.
It is going to maintain, exactly. What if D is flip-flopping between zeros and ones like crazy when CLK is a 0? What's going to happen to the SR latch? What's going to happen to the output X and Y? Absolutely nothing, right? Because when CLK is a 0, it guarantees that the output of the two NAND gates to the left-hand side are going to be ones, right? And we know from the previous slide, if /R and /S are both ones into an SR latch, the output of the SR latch is maintained. So that means when CLK, when the clock signal is a 0, it doesn't really matter what D is doing. D can change all it wants. It's not going to change anything as far as the internal SR latch is concerned. Is that okay? When CLK is a 1, okay, what's going to happen? Let's take a look. So when CLK, when clock is a 1, it basically means it doesn't do a single thing. That's all it says, okay? Because now the output of both of the NAND gates depends solely on D. With the top one, if D is a 1, then this is becoming a 0. With the bottom one, when D is a 1, the bottom is going to be a 1 because this is negated, right?
Yes.
So that means what's going to happen? When D is a 1, we are setting this signal, which we also know as Q. When D is a 0, this is going to be a 1, but this is going to be a 0. But this line is known as /R with an SR latch, which means we are clearing X, which is basically Q. In other words, when clock is 1 and D is 1, we remember it. We change the state to 1. When CLK is 1 and clock is 0, we change the state to 0. We remember 0. When clock is a 0, we do not even pay attention at all to D. We just say maintain the state, don't change it. Is that okay? So this is known as a level sensitive D flip-flop. Okay, so which is also just known as a D flip-flop to be simplified. So the question now is, a D flip-flop is sometimes known as a gated SR latch, and the gate is because of this guy. Which input serves as a gate? I just answered my own question. But just to check whether you guys paid attention or not, which one is the gate? CLK. Yep, there we go. So now we're moving on to the last slide, which also has the worst diagram, which is this guy here. So this one is known as an edge-sensitive D flip-flop. Okay, that's a mouthful. Okay, it's an edge-sensitive D flip-flop, and the analysis for this one is quite a bit harder than the previous one, and I can show you why. Okay, let's go back to the previous one, and I actually misspoke a little bit earlier because I said it's almost like two latches, on top of each other. That's actually not true because this one is not even a latch because none of the output goes back to the input. So that's really just a gate logic for gating the latch itself. Okay, but it doesn't have any feedback. It's easy to analyze. The next slide, on the other hand, has feedback going on with the first level of gates as well. So once you analyze, okay, the analysis of this particular configuration is here. Okay, so I give you all the necessary explanation of what's going on. Okay, but the bottom line is it is an edge-sensitive D flip-flop. This part here, if you just look at this part, is really just an SR latch, okay? Because you can see that there are two inputs, there are two NAND gates, and the connections is exactly the same thing as the SR latch that we saw earlier. And that's also why I labeled these particular lines the same way as we label an SR latch. This is /S/R, X is basically Q, Y is basically /Q. Okay, so this part is easy. This part here, the one to the left-hand side, is a little bit more complicated. So in this particular case, this circuitry will only change the state of these two when we experience a rising edge on clock. Okay, so when clock CLK goes from 0 to 1, that is the only moment that the state of D will determine whether X and Y are zeros and ones or ones and zeros. Is that okay? So that's the function. The way it works is explained here. So, but you have to basically take into consideration of the internal state of the entire thing. You basically, the way you analyze this one is to say, what if /S is already a 1, /R is already a 0, and D is a 1, and then we see a clock going from 0 to 1. How does that work? Okay, and then you have to change the assumption and say, what if /S was already a 0, /R is already a 1, and D is a 0, and then clock goes from 0 to 1, what's going to happen? That's how you analyze this particular circuit. You have to basically start with known state of the SR latch, and then you plug in the input, and then you say, okay, what's going to happen in this particular scenario? Is that making any sense so far? Okay. So this is the final product. Okay, as far as this particular unit is concerned, this particular unit of instruction is concerned, this is the final product, which is a circuitry to remember a single bit. Okay, and the way it changes is whenever CLK has a transition from 0 to 1, then D will determine X and Y, which one is a 1 and which one is a 0. So that means when CLK is a stable one, continuous, it doesn't change anything. D cannot affect the SR latch. Okay? When CLK is continuously a low, a 0, doesn't change the SR latch. It's only when it changes from 0 to 1, then it can affect the SR latch. Is that okay so far? Okay, right. So let me take a look at the time. Okay, we got 10 minutes, which is great. Because now we can look at this and go like, well, this is how we can remember 1 bit. How do we remember 8 bits to remember a single byte? Have 8 of these things, right? And 8 of these things have the clocks all connected to the same point, and then all the D's connect to individual bits from the input. Then you have an 8-bit register. Okay? So what I want to do next is to take a look at a register concept in LogicSim. Okay? So we'll go ahead and start a new one. I can use evolution because this part is really kind of the same between the two versions. And this time we go to memory because the register is, you can experiment with D flip-flops as well if you want to, but I'm going to skip that and I'll go straight to registers. And it doesn't represent registers the same way. It just looks different, okay? But it's really still the same thing, it just looks different. How many people have switched to use evolution? Only a few. Okay, so the rest are still using the generic version. So I'm going to use the generic version. just so that it will look exactly the same as what you would see. So discard. Okay, go back here. The recorder is still going, which is good. Just want to double check. Downloads. Generic. There we go. All right. So when you go to memory and you pick out the register, see how it looks different between the two versions. So this is why I kind of want to stick with one but not the other one, just so that the notation looks the same. Okay, and you can also go to help, go to library reference, and then you go to memory library, and then go to register, and this explains how a register works as far as Logisim is concerned. Yep.
Between Logisim and Evolution, have you had any encounters with the files that are outputted being different? Like, would we have to worry about like putting a file onto Moodle from one or the other, and then it?
Yes, you do. All the existing files that I have pushed out, as far as the processor is concerned, they were all made using the generic version. So if you open it in Evolution, it may not open correctly. So when you do your homework, you probably want to stick with generic at least at this point, because otherwise you will have a mixture of the two, and that may not be good. Yep.
Did you also your 4-bit looking at that, or did you make that in Evolution?
Yes.
So if the browser will take that and use it in the original and export that.
Did it work correctly though?
Some of the notes are changed.
Yeah, you need to massage it a little bit.
Functionally it worked, but also it like just reset the amount of inputs on a lot of the gates, but functionally
Okay.
it still worked.
Okay. Yeah, I think the number of inputs, of the gates, the default has changed, so some of that may not
That's
work.
the only thing I noticed.
Yep. All right. So this is a register, which is basically kind of like a whole bunch of D flip-flops, edge sensitive D flip-flops, kind of chained together. So we'll go ahead and experiment and see how this works. Okay. So there are a whole bunch of pins here. Okay. And it has one additional EN or enable pin, which is missing from our edge sensitive, flip-flop. But other than that, it has basically the same thing. Okay. We have Q, we have D. This is the clock. This is a reset line, which we also do not have. It's just one way to reset the content of a register. So what we'll do, for the next 6 minutes or so, is to take a look at this. Okay, so we'll just have pins to go to each one of these things, and an output pin for the output. There we go, and we'll change everything to 8-bit wide. Well, the input and the output they have to be changed to 8-bit wide. So we connect this guy to here. This is our enable pin. This is going to be our clock pin. And this is going to be our reset pin. This is our output. There we go. And I can obviously label these things correctly so that it has meaning. So this is our EN or enable pin. This is our clock pin, CLK. Oops, I keep doing that. I mean, the cord of the mouse is the problem because I do have a cordless mouse, but the cordless mouse has some other issues. Okay, I'll try out the cordless then. And the cordless has not been charged. Oh, it's off. Okay, now it works. There we go. Okay, so the label for this one is clock CLK. This is our reset. And none of these are negated, so that's why I do not use a slash in front of any one of these. This is output, this is input. Okay, so we got a register. So I want to change the state of the register to something. So let's say we want to change it to C7, okay, in hexadecimal, because this is in hexadecimal. So to change it to C7, I need a 1100 here for C, and the 7 is 0111. We'll talk about how to do the base conversion in some other class, but this is the state I wanted to reflect over here. I want a C7 here. It's not doing a single thing because it is 1, edge sensitive to the clock, 2, enable pin is a 0, okay? So that's why it's not doing a single thing. So because it is gated by the enable pin, it means if I switch clock all day long, it's not going to do a single thing. So I have to make sure that enable is on first. then we can click the trigger, and you can see how the register is now changed to C7, and then the output is also C7, which is the same as the input. Okay, but at this point, I can change the input any way I want. It won't change a single thing in the register because it is edge sensitive to the clock. The clock is now at a stable state of a 1, so it's not going to do a single thing. And because the clock is edge sensitive on the rising edge, okay, when I click on the register, you can see it's sensitive to a rising edge. It means the falling edge is not going to do a single thing. I can do a falling edge, and it doesn't change the output. Okay? And if I turn off enable, then I can clock it all day long and nothing happens. If I want to change the register back to default, which is 0, 0, I can assert reset, and that will change the register immediately to 0. That's how a register works. Okay? And this is the most basic component of memory inside a processor. So what we have explored at this point inside the processor is the ALU first, right? The ALU is the one that does all the computation. And now we have a component that can actually remember something, okay? But it is controlled by these 3 control signals. For the most part, the reset line is not really useful. It is only useful when you power up a computer. You want everything to be in a particular known state. That's what the reset signal is for. Okay, so there's one universal reset signal to every single component inside the processor. So the reset signal, for the most part, is not going to be in a daily operation of the register. The enable pin is important because the clock signal is also universal to the entire processor. So the entire processor has one single clock signal because we need to synchronize the operation of everything in the processor. And as a result, there's only one clock going to everything inside the processor. So the only thing we can really do to control, oh, I want you to update but not you, and so on and so forth, is the use of the enable signal. So the enable signal is individual, okay? Each component, each register has its very own enable signal so that we can say, I want you to update but not you. Yep, go ahead.
So what is the computer really doing when you shut it down?
When you shut it down, you mean when you power up?
Yeah, you don't switch it with the power button, but you do it through the software.
Okay.
Anything to do with the register?
Well, there are multiple levels of power down with modern computers. So you can, when you press the power button, especially in Windows 10, it doesn't really power off the computer completely. So it's not the same thing as, in other words, the components are still maintaining their state, even though you quote unquote power down the computer. If I remember correctly, is it like the control power, or you have to press a control key or some key or alt before pressing the power button for your computer to actually power down in Windows 10?
It depends on what you set to.
Sorry?
It depends on what you have it set to, because you can change.
Right, but the default is not, it doesn't actually do a power down when you press the power button.
Yeah, if it's on a laptop computer by default, it would use like sleep, but if it was like on a desktop, it'd probably do shutdown. At least, well, that's what it was in Windows 8, but I'm not sure in Windows 10.
Windows 10, if you just hit it once, it goes into sleep mode basically.
Yeah.
Okay.
But it will.
But how do you trigger that to go to a complete sleep?
Physically, you hold the button down.
Yeah.
Other than
Yeah.
that,
Hold it down.
If you hold it down, it'll shut off.
In Windows, you can go and specify what the power button does. It has
Right.
different options, so you can say like hibernate, shutdown.
Okay.
Yeah.
And that's why you can power up so fast, because it's actually not completely off to begin with.
Yeah.
Yeah, good. Yeah, question?
Yeah, because I was just wondering, because you could obviously just, hold it and it shuts off, or you can go into the menu and press shutdown and then it takes like a minute or something.
Yeah, when you completely shut it down, it has to make sure the file system is in a clean state, and everything that is cached in the buffer, they have to be written into the file system. So that's why it's taking so long, because it has to tell every single software component, every single process, and say, we are powering down, so you better save everything now. So all of those processes, no matter what they're doing, they have to say, okay, we have to save everything. As opposed to a suspend, when you suspend, it is actually, you're telling the processes and go like, okay, the processor will stop clocking, but memory is still maintained. So every single process is still maintaining all the memory, all the variables, everything that you allocate So, so that's why it's so quick, because, as far as the processes are concerned, there's not much to do, if anything. The computer does have to do something, because, certain components, like the Wi-Fi components, probably has to power down in a particular sequence so that it is no longer active. So when you power up again from a suspend state, it has to restore to that safe state so that your Wi-Fi will go back and connect to the same how do you call that, access point, and so on and so forth. But it is a very small process, but there are very few steps to perform as compared to a complete shutdown. Yep.
What happens if the clock is oscillating faster than the circuits can complete their functions?
That is a good question. Okay, so the question is, what if the clock is going faster then you basically, the state changes can no longer be reliable. In other words, you are halfway through the state change. Okay, let's go back to the slide in the previous one. Okay, so let's go back to the browser. Okay, this is a good slide. So basically what is happening when you're quote-unquote clocking too fast is when you are clocking, when you have a new update cycle, these gates have not completed all the operations yet. And then you're trying to refresh it with a new state, which basically means it's undetermined. It depends on how slow the circuit is, and depends on what the new input is. And that's why when you buy memory, you have those numbers, CAS and so on and so forth. What is CAS?
Like computer algorithms.
No. When you buy memory chips, they have all these numbers, They're measuring delays of memory. Okay, so I know we are running out of time, and I won't give you a new homework assignment just yet because I need to finish the discussion of a register before I give you the homework assignment of the music box. But for those of you who want to look ahead, you can definitely do that. So DDR, CAS. CAS is a column access strobe latency, but nonetheless, the point is it is a latency. So when you buy memory, there are all of these numbers in latencies, but they're all measured in, I think, nanoseconds these days. Okay? And they're basically saying, okay, once you have a signal actuated, how long does it take for it to become effective, to actually make the change? So when you buy memory that is too slow, and you tell your BIOS that you actually have faster memory than that, then sometimes it will work. Because when manufacturers rate these latency, they will use a statistical model. They will test these things and say, okay, 99.95% of the case, it is like this. And they will just pull that number. If you're lucky, your actual memory chip may be slightly better than what it is advertising as at a particular temperature. So the moment you heat up the computer, then it will start to change the characteristic of the chip, the latency will start to change, and it will start to stop working. So put your computer in the freezer. If you stop, this is one of the things that we do in the good old days, is we reverse, those duster thing, air duster thing, if you reverse it, it can become a freezer. So, so we will flip it upside down to spray it on components and see if that will make components start to work again. Then we can isolate the cause of a problem. And little did us know about those cans. The gas inside is not actually breathing air, it is actually toxic to us. So some kids would use it to get high, and others will use it to commit suicide. The worst things would happen to those who tried to commit suicide but ended up with failing organs but not quite dead, because that's really not a very good state to be in. So if you have one of those things, if you want to dust your computer, push all the dirt out, do not use those things unventilated, okay? Take it outside, then you can use it. But when you're inside, try not to use those so-called canned air. I use a blower instead, an electric blower. It is noisy, but at least it's not going to give us some really toxic gas that doesn't smell at all. That is the worst problem. If they make it odorous, it will be better. mix it in with some H2S, great. You check it in just a second. It's like, ooh, that stinks.
They fill them with bitterants now.
What?
They fill them with bitterants now.
They do?
Yeah, I was cleaning my computer one time and then picked up a sandwich and it was absolutely disgusting.
Well, that's better.